Go for it.
All right. Hi, everybody. Congratulations, you made it. This is the last talk of the session. After this, you get to leave. My name is Ryan Marcus. I'm from Brandeis University. Today, I'm here to talk to you about NashDB, which is an end-to-end economic method for elastic database fragmentation, replication, and provisioning. So before talking about exactly what the problems are, what this talk is hopefully going to convey to you is that NashDB is a storage framework for cloud databases and elastic databases. It can be used to automatically fragment your data, to chop it up into pieces, to replicate your data across various nodes, to choose which and how many virtual machines to allocate, and even to route queries to various locations. The key selling point of NashDB is that it tightly integrates an economic model and a lot of nice game theoretic properties into each one of these various decisions, and on top of all of that, it supports query prioritization, which is a feature that we argue is missing from a lot of cloud databases today. So before I get into the details, I want to sort of describe why this is a problem and why you should care about it. In general, distributed database applications require an adaptive approach to fragmentation, replication, and allocation. So classically in the database community, the way that we handle this is either with a hash-based or a value-based data distribution scheme. So at the bottom of the slide here, there's an example of a value-based distribution where some DBA has sat down and figured out, okay, if the value in t.a falls between 0 and 50, I'm going to put that in this particular fragment, and if the value is over 50, I'm going to put it in this other fragment, then I'm going to replicate this one twice, and I'm going to replicate this other one twice. So that's a classic sort of value-based approach. Now, this approach works very well when you have a lot of information about your workload. So if your workload happens to have approximately half the queries run in one of those fragments and approximately half run in the other, this is all good and well and works great. The problem is when workloads shift. Suddenly, your load imbalance will change. You possibly will cross fragment boundaries. A lot of bad things can potentially happen. So if you're a DBA and you're sitting at your desk and monitoring your applications 24/7, then you can see when this situation occurs, and maybe you can do something to correct it real fast. Like maybe you can say, okay, well, I'm going to replace one of these blue fragments with an orange fragments, and now the situation is fixed. Unfortunately, cloud and elastic databases and clouds really kind of rain on this parade. This model of a DBA sitting at their desk updating your database hits a wall when you have modern cloud applications. And the reasons for this are many, many, many-fold. The first is that the number of nodes is not fixed. If your workload gets bigger or changes in some way, you not only have to decide how to redistribute what nodes are doing what, you might have to decide to grow or shrink your cluster. Another problem is that workloads may shift or grow periodically. So that change in workload that caused a load imbalance might happen regularly. For example, at Christmas, you might find that certain products and certain rows in your database are accessed much more often than at Halloween. Or even seasonally, based on 2 a.m., how many people are watching Netflix versus 5 p.m., how many people are watching Netflix. Furthermore, the cost of the underlying cloud resources themselves may change. Over the last 2 years, Amazon has added a ton of different VM types. They've changed their prices a little bit, and spot instances might even change those prices even more often. Additionally, all queries might not be equally valuable. Someone changing their password, you might be willing to accept a longer latency delay than someone making a purchase. And sort of the bottom line for all of this is that moving databases into the clouds makes it cheaper. However, DBAs are not cheap. DBAs have better things to do than to sit at their desk at 2 in the morning and rescaling and reconfiguring your cluster. So this is all sort of the motivating background for NashDB, which is a data distribution framework. It's a set of tools to work with OLAP data sets. It's designed to sit under a traditional database management system and manage a lot of issues with data distribution. One of the biggest grabs of NashDB is that it learns data access patterns in such a way that can create automatic fragmentations. I don't have a super long time to go through all the details of this, so I just want to convey kind of the basic intuition. So for a moment, forget everything you know about fragmentation and partitioning these distributed databases, and instead of thinking like a computer scientist, let's try to think like an economist might. So if I'm an economist and not a computer scientist, suddenly queries are customers who are willing to pay money to access certain tuples, and nodes, again, if I'm an economist, are firms which provide those tuples and have to pay for storage, their uptake, so to speak. So for a very basic example, let's imagine your workload contains one query, and that query is willing to spend $6 in order to read tuples 1 through 5. If you have a single firm, a single node, that provides tuples 1 through 5 and a storage cost of 50 cents, then on average, because there's only one possible firm that this query can go to, this query will give $6 to that firm, which means that firm will make $6 in income, will have an expense of $2.50, and will come away with a profit of $3.50. Now, if you're an economist, you're shaking your head going, there's no way that a free market would ever stabilize to this particular situation. And the key insight is that the profit that that particular firm received was greater than the expenses that that particular firm incurred. And what will happen in a free market, in fact, is that another firm will come along and say, aha, I can make some money here. Now this query, on average, will send $3 to firm 1 and $3 to firm 2. Half the time it goes to firm 1 and half the time it goes to firm 2. The result is that the income of each firm goes down to $3, their expenses are still fixed at $2.50, and they each make 50 cents a profit. Since now the profit is less than the amount of expense, any firm who leaves the system will lose profit, and any new firm that comes in won't make any profit. So we refer to this situation as a Nash equilibrium. So it's a nice theoretical property, and it's a nice way to kind of think about your database and how you manage your fragments. Unfortunately, this talk is really short, so now I'm just going to advertise the things that are in the paper without really explaining them. So one of the first things that we provide is a data structure for tracking the value of each tuple, for managing the demand or the potential cost of each tuple. And we do it in a compact way with very nice log n access time guarantees. We also provide new algorithms that use machine learning to group tuples together into products so that you can deal with them at a smaller level of granularity. Additionally, we provide some replication algorithms that provably result in a Nash equilibrium, so a nice little theoretical guarantee. And we also provide an optimal clustering transition algorithm. So when your workload shifts and you compute, okay, well, here was my cluster before and here's my cluster now, we can show you how to optimally transition the cluster from state A to state B. And finally, we also give a supply chain management motivated query routing algorithm that handles bottlenecks and distributed fragmented data in a way that would make sense to an economist and hopefully now to you too. Also in NashDB, we have a full experimental study, but today I'm just going to show you one little graph that I'm going to attempt to explain. So carrying through with the ideas that we should use economic intuition, we ran this study in the same way that an economist would. And so instead of looking at just query latencies for fixed parameters, we looked at something called a production possibility curve. So essentially what this plot is showing for 3 different systems, NashDB, a hypergraph partitioning based approach like sort or schism, and threshold, which is an eStore-like approach, is the different possible configurations of your system that you could produce. So on the x-axis, we show the average latency. On the y-axis, we show the cost. And each point represents a different configuration of the system. So as you can see, NashDB's points are all in the bottom left, which means that it is Pareto dominant, meaning it achieves either a lower average latency or a lower cost compared to the other systems, which we all think is good and well. So that's it. You can find the paper there at that URL. You can follow me on Twitter. I'm not as attractive as Raul, but I'm also looking for a job, so feel free to contact me about that. The slides are up as well. Thanks.
Thanks very much. Wonderful talk and very interesting. I was wondering if you could give some sense in which how that economic way of thinking actually would work out, in practice. I mean, there's this economic theory which says that, companies come in to take advantage of profit possibilities until nobody makes any profit anymore. I'm dubious about how much that actually applies to the real world. Can you talk a little about how you've seen this theory work out when you actually have companies trying to do this?
Sure. So I'm going to answer your question in 2 parts. First is that my advisor kind of made fun of me for putting a picture of Paul Krugman up here because Paul Krugman disagrees with this idea that firms will always act rationally. But the second thing that I'll say is that comparing NashDB to previous uses of economic models, like famously the Mariposa paper, we don't actually do a market simulation in order to produce this. We analytically solve for the Nash equilibrium and then produce it exactly. So we sort of avoid the race to the bottom or race to the top that can get lost and create rent seeking and all this stuff by sort of asking ourselves on paper, what's the perfect free market equilibrium, and then just instantiating that directly. So while in reality these economic models generally fall very, very short, and you see things like monopolization, we have the unique ability to just be dictators and say, no, there will be 9 firms, and so we avoid those issues.
Thanks for the comparison into economists. And when we talk about money and firms, I cannot stop to thinking depressions. Will that be a similar problem in your system when you'll have to deal with it and how to avoid it?
So one of the interesting non-features of our system is that if you decrease your query priority, your prices, then eventually it can get to the point where it is not economically viable for you to pay the cloud provider to store your data. And this might be what you might refer to as a depression. And so I argued that, okay, well, let's just put a floor on it and say, okay, if the value falls below this, you still have to be one firm, you still have to have your data there. My advisor pointed out, like, look, if your data is not as valuable as the cloud storing it, just delete it. So I guess it would be up to an implementer to decide which of those 2 techniques they feel more comfortable with.
The magic answer is tariffs. Tariffs for everyone. All right? Especially in Canada. Any other questions? All right, guys, this is the end of the session. It's lunchtime. Let's thank all the